So let's look at page 3 of our ionic nomenclature packet. And this is where we're going to get into, I think, one of the toughest aspects, which is dealing with type 2 cations. So these are our transition metals. And they are in the D block, right, in the middle of the periodic table. The other two elements that you're going to see from time to time are tin and lead. They're in group 4, but they're heavy elements, heavy metals, and so they can take on transition metal characteristics, which basically means they could have, there's multiple possible charges here. Now obviously they're only going to have one charge in your compound, and that's kind of the difficult task, is to deal with figuring out what charge a particular metal has in that situation. Now, in this first table, we're going from name to formula. And here, dealing with type 2 cations is not difficult at all. In fact, maybe even easier than dealing with type 1 cations. Because when you go to figure out your ions, it turns out that the charge is going to be represented as a Roman numeral in the name. And so when you see titanium 4 or titanium IV, that means titanium with a 4+ charge. So when you have a type 2 cation, the charge is explicitly given to you. And so gold, which is Au, III, of course, is 3+. Zinc, Zn, II is 2+. Chromium, Cr, Vi is 6+. And cobalt, III, is 3+. And so really, it's just making sure you're comfortable with Roman numerals through 7 is the biggest charge you're going to see. Now the anions here are the same anions that we dealt with before. And so notice that they end in "ide", so they're all monatomic. And so we have fluorine in group 7A, nitrogen in group 5A, iodide in group 7A, phosphides in 5A, and then hydride we've seen before is in group 1A. And so fluoride is F-, right? 7 minus A is 1-. Nitrogen and phosphorus both form 3- ions. Iodide, just like fluoride, is a halogen ion, and it's -1. And again, hydrogen wants to look like helium, so it's just 1-. And then again, to get to your formula then, right, we're just going to cross our charges like we did before. And so we get TiF4 plus 3 - 3. I just need a 1-to-1 ratio, so just AuN. Now, if you did cross, right, you would get Au3N3, but you would want to reduce that down to a 1-to-1 ratio. So remember, ionic formulas are just ratios. You want the smallest possible ratio. For zinc iodide, BZNI2. Notice here that the 3 and the 6 are multiples of each other. So if you cross, you're going to get Cr3P6. But again, a 3-to-6 ratio can be reduced down to a 1-to-2 ratio. Right? And remember, if you don't reduce your ratio, then anything's, right, acceptable. 18 and 36, 24 and 48. Those are all 1-to-2 ratios as well. And so the rule is, we don't know how many ions we have, we just know the ratio of cations to anions. We want to make that as simple as possible. And then for our cobalt 3 hydride, it would be COH3. And so the tougher aspect is really going to be figuring out the charge from the formula. And so, again, we're going to go back to the skill that we talked about on page 1, which is uncrossing our subscripts. But now we need to be a little bit more careful. And so let's talk about some of the considerations here. First things first, right? Again, we can uncross our subscript. So let's come down here and look at these examples with vanadium. Vanadium can take on several different charges. And so when you uncross your subscripts, right, this 5 on oxygen came from vanadium. This 2 on vanadium came from oxygen. So what this is saying is if O is going to be 2 minus and vanadium is 5 plus. What you want to do, though, is you want to check your anion charge and make sure that it's right. O is 2 minus. And so in this particular case, I know that I am dealing with a 5 plus charge on my vanadium. The other thing that you want to be on the lookout for is your 1-to-1 ratio. Remember that in this scenario, the cation charge is going to match your anion charge. And so I know, for instance, that nitride is 3 minus. I just saw it at the top. And so in this case, I know my vanadium has to be 3 plus. So we always know the charge on the anion. There is no varying anion charges. And so in this case, I'm dealing with 3 plus. The other thing that we want to be careful of is with polyatomics, right? If you have parentheses, that means you have more than one polyatomic, and you can attribute maybe that subscript to your vanadium. But if there are no parentheses, that means it's an understood 1. And so this last scenario is a 1-to-1 ratio as well. And so what I want to do then is I want to figure out the charge on my anion, which is, in this case, PO4, which is a polyatomic. It's known as phosphate. It's always 3 minus. And so my vanadium here has to be 3 plus. So it's the same scenario as my VN. A 1-to-1 ratio with an anion that's -3. My vanadium has to be +3 to balance it. Now, the last thing that we have to be careful of is what we have here with our VCO3. If you were to uncross charges, again, this 3 could be thought of as coming from the vanadium. And the understood 1 here on vanadium would come from my CO3. The problem is carbonate is not -1. Carbonate is -2. So this is a scenario where my ratio has been reduced. By what factor? Well, by a factor of 2. And so my vanadium here has got to be scaled up by the same 2 times. And I actually, in this case, have vanadium that's 6 plus. So again, you got to look out for those situations where you have multiples. And that's far more likely with transition metals because they have bigger charges, right? We have +4s and +6s. Whereas with main group, right, really it's the 1-to-1 ratios you have to watch out for. And so if you have 2 and 4, 3 and 6, 2 and 6, you're going to have a reduction that takes place. And so the one thing that I kind of do is when I am going from formula to my ions, right? And again, the idea here is we're uncrossing. The first thing I really want to do is I want to look at my anions. And I want to utilize what I know about my anions. So again, we have I, P, Br, Se, and Cl. And I know what those charges are based on their location on the periodic table. I know iodine's -1. I know phosphorus is 3 minus, bromine's -1, selenium's 2 minus, chlorine's 1 minus. And so when I look at my formula and I look at the subscript on my metal, I want to see, does it line up with my anion? In the case of iodine, bromine, and chlorine, it does. And so those are situations where I can simply uncross to get my cation. And so this 4 must have come from my lead. This 2 must have come from my cobalt. And this 3 must have came from my titanium. Now, the other 2 scenarios I got to take a look at, right? Here, in MnP, I notice that I got a 1-to-1 ratio. I know phosphorus is 3 minus, so my manganese here has to be 3 plus. Now, if we deal with CrSe3, the fact that I know selenium is 2 minus, along with the formula, lets me kind of think about it in a different way. That formula says that I have not 1, not 2, but 3 Se2 minuses, which is a total negative charge of 6 minus. I only have 1 chromium that has to balance out that 6 minus, so it has to be 6 plus. So I can think about it in terms of total positive and total negative charge. Again, you can kind of think about how when those have been crossed, you get a 6 to 2, or a 2 to 6 ratio, which is the same as a 1 to 3 ratio. Now, going from ions to name, remember all we have to do is name the ions. And again, we're going to start with the cation, which in this case is going to be the metal. So lead, manganese, etc. But keep in mind, with the transition metals, type 2 cations, we have to use a Roman numeral. So to represent 4, we do IV. To represent 3, we do I. Again, these are capital I's, not lowercase l's. Here we have cobalt. And so we have cobalt II to represent cobalt with a +2 charge. Chromium 6 would be Vi. And then titanium 3 would be III. And then for our anions, again, we just use our element stem plus the IDE ending. So iodine becomes iodide. Phosphorus becomes phosphide as an ion. Br minus is bromide. Selenium becomes selenide. And chlorine is chloride. So again, take your time, do your due diligence, check your anion charge to make sure that you are on the proper path. All right, let's move on to polyatomics.